All right, so you should have gotten your group work back. Yes, you got your group work back. Yes, we are good. You can read my comments for the most part. Okay, excellent. All right. Nothing is due until, I feel like May 1st is our next due date, but I'm not positive. Don't quote me on that. Look at the email that I sent out yesterday for sure. That has the correct due date in it for the homework from chapter 5, the first part, 5.1 through 5.3. Okay. I don't know that I have anything else. Procedural, etc. Anything else that people have questions on at this point in time? Anything? No? We're good? All good? Okay. All right, then. Here's the plan for today. So, yesterday, systems of differential equations. Yes, one independent variable, two or more dependent variables. Remember, if you have two independent variables, that is partial differential equations. And while that is a good and beneficial subject area, it is not mine. And I will probably never teach a class in partial differential equations. I've never taken a class in partial differential equations. So we are sticking with one independent variable. And yesterday we just kind of played around, right? That was what we did yesterday. We played around. We said, man, we can probably figure some of these out, kind of, sort of, maybe. Yeah, we need a more systematic method. So that's today. That's our more systematic method. It's called the method of elimination. So let's get that going here today. Section 5.2. We're spending 2 days on section 5.2. And fair warning, today is heavy in, I don't know, development. We're maybe going to do one example today, but we won't do a lot. We're going to do more examples tomorrow. We've just got a bunch of stuff to develop today. So I need you to hang with me. And then I promise that we will do examples again, maybe one today, but tomorrow for sure. So section 5.2, once again, is the method of elimination. Okay, so let's start with a problem that you know how to do. And this isn't differential equations. This is just regular, normal system of equations. For example, if I have 8x plus 2y equals 4 and negative 5x plus 5y equals 8. 8x plus 2y equals 4 and negative 5x plus 5y equals 8. If we are doing elimination, we have a couple of different choices. So step or method number 1, we could multiply, I'm going to call it equation 1 by negative 5, multiply equation 2 by, we could either do positive 8 or negative 8, it doesn't matter. We'll go with 8 and then subtract. I think it would be subtract, I don't think it would be add. So we could do that if we wanted to, and then this is something that would allow us to eliminate the x's, right? Do you see that in your head, taking a quick glance, right? If you multiply equation number 1 by negative 5, equation number 2 by 8, and then I'm pretty sure it's subtract, then you will get rid of the x's. Yes, we're seeing that, get rid of the x's, okay? We could also say, or, I'll call this step number 2, but it's really method number 2. We could multiply equation 1 by 5, equation 2 by 2, and then once again we could subtract, and this would allow us to eliminate y. So if we multiplied the first equation by 5 and the second equation by 2, and then we subtracted, that would allow us to eliminate y. This is high school algebra, maybe 8th grade. But high school algebra should be familiar with this. This is method of elimination. We're trying to get rid of one of our variables. All good? Everybody good up to this point? Okay. All right. So we can also apply this method of elimination to differential equations, except we've got a little more going on than just constants in front of our variables. So if we want to use the method of elimination for differential equations, we have to figure out how to represent derivatives. Here's an example, and I'll show you what I'm looking for. So let's say that this is my system of equations. X prime equals x minus 2y, and y prime equals 2x minus 3y. X prime equals x minus 2y, y prime equals 2x minus 3y. You could do this the way we did yesterday with messing around, and if we were in class and I had a better gauge of how long this would actually take you, I would probably have you do this one as a introductory step to play with this, mess around like yesterday. We'll skip that step because I want to make sure I get through as much as I can today. So you can play with this if you want. The solutions in my notes, you can come up with how are you going to get to one equation with just one of the x's and y's. So you can play with this the way we did yesterday. The other thing we want to do is be more systematic. So in the equations that we had in the previous example where they were just algebra, we had all our variables on one side and all our numbers on the other side, right? All our variables on one side, all our numbers on the other side. So we want to do that same thing here. We can get all our variables on one side and all our numbers on the other side. And if I regroup, that's going to give me x prime minus x minus 2y equals 0 plus 2y, x prime minus x plus 2y equals 0, and negative 2x plus y prime plus 3y equals 0. I'm going to just move that equals 0 in the top equation so that everything lines up nicely. Okay, so we've got x prime minus x plus 2y equals 0, negative 2x plus y prime plus 3y equals 0. Here's where we've got an issue. It doesn't look exactly like the algebraic equation that we had in the previous slide because we've got derivatives and we've got constants. So we do have these two x variables here, but one of them is x prime and one of them is just a regular normal x. We need to figure out how to deal with that. And the way we want to deal with that is use what's called a linear operator. So we are going to denote x prime as d of x. We're going to change our notation a little bit. You'll see why in just a sec, I promise. Instead of saying x prime, we're going to use a capital D. And sometimes we put parentheses around the x, or sometimes we don't. Either way, one of the two. This is called operator notation. We talked about this a little bit earlier in the semester, but I didn't hit it as hard as I sometimes do. So we're going to need to just review it right now. Operator notation puts a function as input and gives you a function as output. So my input is x, my output is the derivative. That's it. That's all this is. Input is x, output is the derivative. All right, so we can rewrite this again. Here's what we've got. Dx minus, I'm going to write this as 1x, you'll see why in just a second, plus 2y equals 0. That's my first equation, right? My second equation is negative 2x plus dy plus 3y equals 0. So I can write those using capital D's instead of with primes. That looks more complicated, but I promise there's reason for doing it that way. So I can write those with capital D's instead of with primes. And then what I can do is kind of sort of factor out an x and kind of sort of factor out a y. So I can say d minus 1 x plus 2y equals 0. And I can say negative 2x plus d plus 3y equals 0. I can kind of sort of factor out the x and I can kind of sort of factor out the y. I'm being imprecise. And for probably the 5th time this semester, if Dr. Brown were teaching this class, she would be way more precise because this is an analyst's way of doing things. But being a little imprecise. Yes, it is magic. We're doing a little bit of magic. We're being sloppy with the math. And I, as an algebraist, don't really care that we're being sloppy with the math. It's magic. It works out. It's great. Dr. Brown can tell you way more about why this is actually legal and why you're actually allowed to do it. Okay, before we keep going, are we okay up to this point? Doing good? Everybody's good up to here? All right, so now we can do step 1 and step 2. So we can do the same thing that we did before because we've got coefficients on x's and coefficients on y's, and we can multiply through and subtract. So let's do step 1 and step 2, and we'll see what happens here. So step 1 is going to be multiply equation 1 by -2, multiply equation 2 by d minus 1, subtract, and eliminate x. Do we see it? Do we see where that's coming from? If you think about the algebraic equations that we had on the previous slide and the differential equations that we have on this slide now, multiply equation 1 by -2, equation 2 by d minus 1, subtract, and that will let me eliminate x. Or, if we wanted to, we could do step number 2, which is going to be multiply equation 1 by d plus 3. Sorry, you guys are over my example. D plus 3. Multiply equation 2 by 2, subtract, and eliminate y. You could do it that way. Doesn't matter, step 1 or step 2, either one. And we're actually gonna do both and see what happens in just a second. But that's the way that we can get rid of our x's or get rid of our y's. So let's try this. We're gonna do step 1 and we're gonna do step 2. We're gonna do both and we'll just do them separately, one at a time. So we were at, sorry, this is where it would be helpful to have previous slides. D minus 1x plus 2y equals 0 and -2x plus d plus 3y equals 0. So if we do step number 1, I am going to get d plus, or -2 times that whole first equation, d minus 1x plus 2y equals 0. I'm writing this out in painstaking detail this first time, and then we're not going to do it in as much detail after this. But -2 times that, and then I also get d minus 1 times my second equation, -2x plus d plus 3y also equals 0. Technically, this first 0 is -2 times 0, right? Because I really do need to multiply both sides of the equation by -2. It's still 0, but -2 times 0. And technically, the second one is d minus 1 of 0, but that's still 0 also. So sometimes it'll make a difference, not in an example we do today, in an example we do tomorrow, it'll make a difference, not so much today. Okay, so let's multiply out. Here's what we have. If we rewrite, we've got -2d plus 2x minus 4y equals 0, right? If I distribute that -2, -2d plus 2x minus 4y equals 0. And then we've got -2d plus 2x plus d minus 1 d plus 3y equals 0. So I'm multiplying out the first one. Notice that my coefficients on x's are the same. That's good. That's progress because now we can subtract. That is going to help me out in my method of elimination. This is good. And I'm going to subtract, but I'm going to subtract the first equation from the second equation because that will let me deal with less things being negative. So I end up with d minus 1 d plus 3y plus 4y equals 0. If I subtract that first equation from the second one, I'm just going to subtract in the opposite order in order to make this a little bit easier to deal with. Okay, some more magic. Here we go. Again, I'm cheating. I am cheating, but we can FOIL. So we can do d squared minus plus 2d minus 3 times y plus 4y equals 0. Not exactly legal, but close-ish. D squared plus 2d minus 3 plus 4y equals 0. If I FOIL those first two pieces, and then I need you to remember d meant a derivative, so d squared means a second derivative. D meant a derivative, d squared means a second derivative, and I'm doing it of y. So what this is going to give me is y double prime plus 2y prime minus 3y, and then we've still got that plus 4y equals 0. D squared is a second derivative, d is a first derivative, and a constant is just a constant, that's it. Y double prime plus 2y prime minus 3y plus 4y equals 0. This we know how to solve. Y double prime plus 2y prime plus y equals 0. Normally your next step would be characteristic equation. I won't write it out, I'll just write the roots. So R1 and R2 are both equal to -1, all good, and that gives me my value of y. C1 e to the -2, or C1 e to the negative t, right? Remember my independent variable is t, plus C2 t e to the -t. That's y. Yay! We solved for one of our two solutions, one of our two dependent variables, and we did it in a systematic way. This is good. We like that. We like a systematic way. What I want you to do is execute step number 2 for me. So I want you to do this again and execute step number 2 in order to be able to find x. If you eliminate y, you'll be able to find x. So new slide. And we're going to do step number 2. So once again, we've got, going back, d minus 1x plus 2y equals 0. Negative 2x plus d plus 3y equals 0. Do step number 2 for me and see if you can eliminate y and get an answer for x. So do step number 2. Think about what you want to multiply by and then eliminate y. Go ahead, do that. You do actually get the same roots in this case. So you should get the same roots, and you can't use C1 and C2 again because we use those in Y, and we might possibly have different constants. So you got to go to C3 and C4. You can't use the same constants as in y. They might be different. So we need to say C3 and C4.